Morning once again, students. Hope you're all well. Today I did a video of me wanting to explain the concepts of clipping. Of me explaining the concepts of clipping. Do you expect that in case the big blue button does not help us today, that you at least I will be able to explain these aspects of clipping. So that's what we are looking at today. Clipping. And so far, we've been able to look at various aspects involved in graphics. We've been able to review aspects of rasterization or line scan conversion, line drawing. We've also been able to look at projections and transformations, which are really key aspects involved in graphics. One thing I would like to urge my students is that we are reviewing the fundamentals or the building blocks behind computer vision display. And these are the building blocks. So once you're able to understand what is rasterization, what is scan conversion, what is clipping, how is it applied, then you can go further ahead and be able to create your own display aspects, which that one will be in further aspects, display aspects which you could use in various scenarios in the world. So today we are looking at clipping, and clipping is a very important technology involved in graphics. And clipping is purely like removing unwanted regions, not necessarily unwanted, but regions which are not covered within the viewport or window port. That's what clipping is. So for example, I usually like giving this example of when you're using your mobile camera or your mobile phone to take a photo, and usually have the camera port or the lens port or the viewport. And that camera usually, when you're looking through your mobile camera, there's usually a box, and you try as much as possible to fit everything or everyone within that window frame. So that is what we call a viewport. So that is the viewport which we have for the camera, and through that viewport, we are able now to be able to get a good picture and be able to capture everything that should be within that picture. So clipping is purely along those lines. So it's usually removing aspects not covered within. So it's actually removing aspects not covered within, or not covered, or not captured in the view or view window. So that's what clipping is all about. So you're purely removing images or parts of images which are not covered within your view window. So that's what clipping is. So it's a key element in graphics, because one thing we have to understand with our graphic display devices is that they have limited. So graphic displays have limited display capacity in terms of size. And thus, we need to only capture those key elements that are captured within the view window to be fitted within our graphics, within our graphics element or device. The same way, if you're looking at projections, and a good example I've given is that of a picture, because our camera cannot be able to capture everything. So we try as possible to fit everything within the view window of our camera. If anything is outside the view window, it will be clipped. If anything is within, it will not be clipped. So clipping, basically, we are talking about the aspect of removing aspects not captured within the viewport. Now, there are various key terminologies. The key aspects in clipping. The first one is the window. We have to understand what is the window and how it is used. We have to know the in codes and out codes. Thirdly, we have to know types of clipping and how each is performed. And then fourthly, we shall discuss the algorithms. As used in clipping. So that's the first thing which we need to understand. What is clipping? How is it applied? What are the key aspects involved in clipping? So we need to understand, first of all, what is clipping and how is it applied? Okay. So if I may share my screen. You share. So let me share this. So because you're talking about clipping, so clipping basically, we have to look at clipping and clipping algorithms. So clipping, we have to talk about 2D scan conversion of line segments and polygons. So what event points or line segments or vertices of polygons lie outside the visible device region? So remember, that's what I said clipping is all about. It's all about ensuring that aspects within the visible device region are displayed and anything that is outside is not displayed. So you need clipping. So I'll share those notes. So clipping basically is remove points outside region of interest. Usually call it a clip window. And we have primitives to clipping. We have 3 of them. We have point clipping, line clipping, and polygon clipping. So we shall be mostly be interested in line clipping and polygon clipping. So line clipping, basically, you look at a line and decide, does it lie within the clip window? If it doesn't, then you automatically clip. If it lies within the clip window, then you do not clip. But you have those 3 variations. You have point, line, and polygon. So one thing we have to understand is that most of us are aware. Remember, and that's how I said it's a building block. Even if you look at the way we have started looking at these algorithms, we started with line drawing, and line drawing is basically a parametric equation, which is in the form of y is equals to mx plus c. That is the way we define a straight line. Now, when you're clipping, you shall be clipping according to the coordinates of this line. Remember, we are drawing a straight line. So if you're drawing a straight line, anything that is defined in graphics is defined according to the equation of y is equals to mx plus c. And various lines lead to polygons, and polygons leads to the definition of images that we are having in a graphics image. So when we are doing this clipping, we shall be clipping it according to the parametric equation, and that's when we have the left clip and we have the right clip and everything. But this one is not of any importance today because this whole procedure was improved, and that's why we had an aspect of looking at in codes and out codes, which we shall be looking at. Now, clipping a line segment, there are 3 case scenarios. If the line segment is entirely inside the clip window, you keep it. If it's entirely outside, you discard it. If the line segment is partially inside and partially outside, so you generate a new line to represent the part that is inside. Now that's where clipping now comes in. If the line is entirely inside the clip window, you do not need to clip. If it's outside, you do not even need to clip because you won't display it. But if it's partially inside and outside, then you need to clip. Now, in the third scenario, this is where clipping usually occurs. So there are various aspects which we look at when we are clipping, and the first aspect we usually look at is when we are looking at something we call out codes and in codes. And share something here. So we are talking about line clipping. So when we are talking about line clipping, then we have to talk about strategies for clipping. And I've talked about the three of them. If it's outside, you don't display it. If it's inside within the clip window, you display it. If it is an intersection, if it's partially inside or outside, then you have to clip where that line occurs. So clipping is basically like that. So for example, if it's within the clip window, like this one you show it. This one is totally outside, so you do not even need to display it. Now, this scenario, this one and this one, you'll need to clip, and you need to clip based on the endpoints. And that's why I was saying on the intersection endpoints with the drawing area or the clip area. And that's why we work with coordinates. So as you see, the strategies are check inner loop. If point is inside, you don't clip. But if it's within the intersection of a boundary, then you clip at the intersection of the boundary. Now, as I was saying, now this is a good scenario of possible configuration. Like, let's look at line AB. Line AB is within the clip window, so we do not need even to do anything. We display it. EF and GH are outside the clip window, so there is no need of displaying it. We do not even need to clip. Now, the only problem we have is with IJ and CD. Now, with IJ and CD, we have to clip. Okay, so in essence, you clip at intersections, at intersection points. So you clip here and here, and then you create new joints. So when I clip here and here, so it means that here I'll have I and here I'll have J. C will still remain intact, but here I'll have the new D. So that's the basic algorithm which we have to do. So the basic algorithm for line clipping, we usually use something we call the Cohen-Sutherland. So line clipping is purely based on the Cohen-Sutherland. So the basic algorithm of the Cohen-Sutherland is you accept lines that have both endpoints inside the region. The first one, like A and B, we accept both them. The second one is we reject lines that have both endpoints less than X minimum or Y minimum. We reject lines that have, so one thing, we reject lines that are not within inside, we reject lines that are not within the clip window. So one thing is that for this one and this one, we trivially reject because it's not within. Now for this one and this one, we test. We clip and retest if it's within the clip window or not. All of this, we clip and retest whether they are found. So the third way is you clip the remaining lines at region boundary and repeat the previous step on the clipped line segment. So meaning that I'll come to this line, I will clip here and here, and then I will retest. Is it within the accepted region? If it is, then I accept. CD, is it within the accepted region? Yes, then I'll accept. Now, these two I have clipped. Is it within the accepted region? Then I will trivially reject. Now, the way this algorithm works, Cohen-Sutherland, or any clipping algorithm, the way it works based on what we call the in codes and the out codes. So in our clip window or in our viewport window, we usually assign a 4-bit code to each endpoint. So these are 4-bit code. And the clip window is usually represented by this 4-bit code of 0, 0. So we have to look at this and I have to understand what does each of these bit code usually mean. So the first bit code, if Y is greater than Y max, then it's represented here. Okay, so we have to test. So let me just open up some other an aspect which is sorry, is recording. So windows and clipping. Remember I said that we have a window and a viewport. So I was talking about the coordinate system. So we have the Cohen-Sutherland line clipping. So we have inside and outside window codes. Remember I said this is one of the key aspects that will help us dispense this phenomena. Remember the phenomena which we were talking about? The phenomenon which we are talking about is this phenomena of determining, does it lie within, if I was to use this scenario, does it lie within the viewport or not, or the clip window? Does it lie? So the only way we can be able to do that is if we talk about the inside and outside window codes. So to determine whether endpoints are inside or outside the window, the algorithm sets up a half space. So that's how the Cohen-Sutherland algorithm usually works. So it sets up a half space. In this half space, actually, anything that is inside the window, it's called the inside code, and anything that is outside, it's called the outside code. And that's why, remember, we divide it into various regions. So this is the window. Anything that will be inside our window will be displayed. Anything that is outside won't be displayed. So that's how we usually, we generally assign the regions. And then we clip according to the regions. Okay? So how do we set it up? Okay? Each bit code is set to either 1, true, or false. If the region is to the left of the window, the first bit of the code is set to 1. If the region is to the top of the window, the second bit is set to 1. If to the right, the third bit is set to 1. If to the bottom, the fourth bit is set to 1. So basically here, what it means, left, the first one is set to 1. So this is the left of the window. Now, right, if the third bit is set to 1, where is right? If the left, the first bit is set to 1. If the region is to the top of the window, the second bit is set to 1. So here's the first bit. Here's the first bit, which is what? Which is left. If the region is to the top of the window, the second bit is set to 1. So the second bit. So this is the top. If the third bit is to the right is set, the third bit is set to 1. So the right is basically where the third bit is set to 1. So this is left, set to 1. First bit is set to 1. If the region is to the top of the window, the second bit is set to 1. So second region is the top. And to the right, the third is set to 1. So the third. Actually, here there's a repetition. So this is the first bit. When you're counting bits, you start from here. Start from the left. First bit, there it is. And then you come to the window. But now the thing is here, the region is the top of the window, the second bit is set to 1. While the 4 bits then identify the 9 regions. So what it basically means is that we have arranged the window like this. The only thing we need to remember is that the window code is, the in code is 0000. So anything that is within this 00 is displayed. Anything that is outside the 00, depending on its arrangement towards the window, it might be clipped or not clipped. So this statement is really important so that you can understand where's the left, where's the top, where's the bottom, and where's the right. So basically, the left is usually the first bit code is set to 1. The top, the second bit code is set to 1. The right, the third bit is set to 1. And the bottom, the fourth bit is set to 1. So here you see this is the fourth bit, this is the first bit, this is the third bit. We can look at it. First, 1, 2, 3. So first bit, that is the left. That is the left. The region at the top of the window is set to the second bit. So the second bit is the second bit. The first bit, the second bit. So there's the top. And then to the right, the third bit is the right. And then the bottom is set to the fourth bit. So this is left, right, top, bottom. Because our window is usually inverted. Remember, when you're looking at a camera, anything that you view is outside there, it's usually inverted within the camera, within the image, or within the display device. So we have to have that aspect. So left, right, top, bottom. Okay, like that. Yeah. The fourth bit is set. So left, right, top, bottom. Remember that. Left, right, top, bottom. Usually like that. So that's how it usually is. So the sequence of ordering is usually left, right, bottom, top. That's how it usually is. So we perform the logical AND operation, determine if the codes lie within or outside the window. So given a line, if you're given a line, you check the outcode. So for example, if I'm given this line, I'll have to check, does it lie within or outside? This one we trivially accept it because both its endpoints are within the window. E and F are outside the window. G and H we clip and we test again. I and J we clip, C and D we clip. So when we clip, we come and redo the test again. Does it lie within the window? If it does, we accept it. And we accept based on the new points that we are having. So this one is the most, it is the easiest algorithm, okay? So here, you compute the 4-bit code for each endpoint. So it's really, if both codes are 0, 0, so it completely lies inside, okay? If both codes have one is not 0, 0, then the lines lie outside the window. If a line cannot be trivially accepted and rejected, at least one of the two endpoints must lie outside the window and the line segment crosses a new window. The line must be clipped at the window edge before being passed to the drawing. So you examine. That's what I'm saying. If it's like this one, we clip and then we re-examine again. CD, we clip and re-examine again. That is what it was being said in this other one here that we are having. In this other one that we are having here. Okay. So we have to basically accept, and that's why I said it works with in-codes and out-codes. So we have to test. We have to test, where does this thing lie? Okay, where does this thing lie? So the coherent Sunderland choose an endpoint using the clipping region, clip to a boundary region, consistent ordering, and then set the new line to have endpoints and new intersection. You may need to run this a few times on a single line. So for example, let's look at this example. So we have the line FE, we have the line GH, we have the line CD, and we have the line JI. So, so we have AB. AB, we just basically do an AND operation, an OR and an AND. So we have the line 0, 0, 0, 1, and 0, 1, 0, 0. So that's where it usually lies, or this one. And when you clip, so this one, it does not lie within the region, so we remove it. We come to CD. CD, we come here, we check it. The first one is 0, 0, the second one is 0, 1, 0. So meaning AND or 0, so it means that AND, so we clip here the intersection. EF, it's 0, 0, so we accept. GH, 0, 0, 0, 1, and so we clip. And which one else? IJ, we reject. You see, now IJ, we reject. IJ, we trivially reject because it's outside. When you do a combination of AND, we reject. So here, basically what it means, you have to do a what? You have to do an operation to get the outcome. So here we trivially accept it because, remember, when we do the AND operation, it gives us a 0, 0. So it may seem that the algorithm or the line is within the clip window. So we need to come and trivially test it again to check. So we clip here and here, and then we come and find that it's outside. So we totally reject. So that's why I say, you see now, it keeps on repeating the algorithm. So the first time we do the test of all the lines, we do the AND operation. And the AND operation is whereby you take this and this, we get the AND is that. So we clip. We take this and this, that is for CD, and then we get the AND operation, we clip. We take E and F, we get the AND operation, we accept. We take G and H, we take the AND operation of these two parameters, that is 0, 0 and 1, 0, 0. We get that, we clip. Now, I and J, we totally reject it, because if we take the AND operation of this and this, we get that. So it's rejected outside. Now we come and do another pass. Now we clip here and here. And now I said, now when we clip it here and here, now we do the AND operation, we get it is the AND operation of 0, 1 and 0, 1, we get it 0, 0, 1. So we reject this whole line. Now CD, where is CD? CD is 0, 0 and 0, 0. So we accept. So it means that we accept up to here, this point, and everything outside we reject. GG, we accept up to here. So everything up to here, we reject and we accept the rest one. So we continue like that. So if an endpoint has a code of 10, the logical AND would be 100, which indicates that the line segment lies outside the window. If an endpoint has codes, the logical AND would be, and the line could not be trivially rejected. So that's why you see, like this one, the logical AND of why you could not reject A and B is because the logical AND of A, where A ran and where B ended, if we took the logical AND of 001 and 0100, we got 00. And that's why we could not reject this one. So we had to come and perform another test here so that we could be able to know where does this line end. And when we knew where it ended, then we rejected. So one thing you have to remember with Cohen-Sutherland is that we look at the endpoints, where the endpoints start and where the endpoints end. So for this 00, it starts here and it ends here. So that's why you could not reject it. But now the second one, it starts here and then it ended here. So we take this and this, and then we trivially reject that because the logical AND, so this is the old A, new A, because it's still within the 001. So we reject that line because one of the endpoints is totally outside the clip window. So we could not accept it the way it is. So the Cohen-Sutherland usually works on that aspect. So that is the first one, the line drawing algorithm of the Cohen-Sutherland. It uses in codes and out codes. So that's line clipping. So I want us to see the difference. So line clipping, you have to look at the window. You must have a window. And I was giving a good example of a camera. Your phone camera, the way it uses the basic principle of line, the Cohen-Sutherland clipping algorithm, whereby everything outside, if you're taking a picture, and even if I'm steady, anything that is outside my view window will be automatically clipped, even if I see it. And remember, we have those two viewpoints. We have a window, which is in the world coordinate system. This is the window. And then we have our view window or a viewport. So even if I'm looking at you as a whole you, but I take my camera to only take part of your body, then only that part of the body will be seen in the camera. So that is the Cohen-Sutherland line clipping algorithm. We have also the other one, the Liang-Baskai line clipping. And or the Cyrus-Beck. We usually call it the Liang-Baskai or the Cyrus-Beck. So it has been optimized for an upright rectangular clip window. So the other type of algorithm, although this one I won't look into it, this one I'll leave it up to you to go and read on it so that you could understand how it works. And I want you to tell me the difference between this algorithm, the Liang-Baskai line clipping, and the Cohen-Sutherland line clipping. Okay, how do they both function differently? The other interest would be with the Sutherland-Hodgman polygon clipping. Remember I said that we have three types of clipping. We have point, we have line, and we have polygon. We have discussed line. Line and point usually go hand in hand because with the line clipping algorithm, we see the only way we can clip a line is if we test the point codes of that line. If those point codes are within the viewport, then we do not clip the line. If they're outside, then we clip. The other one is the Sutherland-Hodgman. And the Sutherland-Hodgman is used for clipping. Now, the Sutherland-Hodgman has 3 scenarios. You clip at polygon according to its vertices. Okay? So what do we do? It basically follows 4 steps. First, you clip the left side of the window. Then after you've clipped, you come and clip the top side of the window. Then it has clipped, you come and clip the right side of the window, and then you come and clip the bottom so that at the end you get your image. Okay. So it basically, that's how it usually works. You start from left, top, right, bottom. Left, top, right, bottom. Always remember that. And it does that because it has 4 types of edges. No, we have a clip window, okay? So the algorithm goes around the edges of the window, clipping the polygon. It encounters 4 types of edges. So all the 4 types of edges are represented here. So number 1, edges that are totally inside the clip window. So this one is the first one. So you add the second inside vertex. The second one, this number 2, edges that are leaving the clip window. So here, these are edges that are leaving the clip window. And then number 3, these are edges that are totally outside the clip window, and 4 edges that are entering the clip window. So, like for example here, the first one, A, because we start from the left. So it leaves that this edge is leaving the clip window, so we remove it. This edge is also leaving the clip window, that's the top, and then this one is removing, and this one is entering. So the way it is, this image, if it's coming into the view window, it is coming like this. So if it's coming like this, then it means that we clip here, we clip here, we clip here, and we clip here. So according to these 4 edges, 4 types of edges we have. Totally inside, that is represented by 1. 2, those that are leaving, and we clip the ones that have already left. 3, those are totally outside. We don't even recognize them. And 4, those that are entering. Serve the intersection and inside points as vertices. So how to calculate the intersection? So we have the vertices x, y. So when you talk about vertices, so these are vertices x, y, x, y, x, y. The corners, those are the vertices against a clip window. So you must have a clip window. Remember, you must have a clip window. And then you look for the intersection of those clip window. So the location of our vertice x, ix, and iy of the intersection edge is, the intersection of x must be equal to the x minimum, and the intersection of y must be given by the slope, where we take the intersection coordinate, we take the gradient, and we look at the scope. So basically, this is purely the mathematics that is involved, although we are not highly interested in that mathematics. I was just highly interested in letting you know how it clips. So in essence, the Cohen-Sutherland has to perform those 4 variations. It looks at this vertex, and this vertex, and this vertex, and this vertex. This is the whole left side. So it looks at this whole left side. Where shall I clip? It clips here. And then it creates a new vertex and a new vertex. It comes and clips here on the top, creates a new vertex. Comes and clips here, creates another new vertex. Comes and clips at the bottom, creates a new vertex. So generally, that's about clipping in a nutshell, if I could explain it in a nutshell. And the work would be, and I'll give this as part of the forum. I would like you to discuss the difference between the Liang-Barsky line clipping and the Cohen-Sutherland line clipping. So I'll share these notes. I believe this book you already have it. Looking within the first topics we had, the docs, this PDF, I've shared it already. You already have it, so you can be able to look for that work. The others I've already shared with you. So I'd like to stop there for now, and kindly check on that.